It's day 77, chemistry fans, and we just took our equilibrium test, and now we'll be taking a look at why I have heartburn. And it all comes down to these things called acids and bases, so we're going to play a little bit of proton football today, which makes it pretty straightforward, because we just did an equilibrium unit. Now, cool things that we should notice, some people struggle with equilibrium. Remember that chemistry is chemistry. It also, of course, is chemist, try, and think. So you have to spend time making sure that you understand the concepts. If you really paid attention during the equilibrium, acids and bases will be amazingly easy because it's all about, of course, reversible reactions. And all reactions are reversible. Now, key things we're going to take a look at now is we're going to dig into this simple reaction. You should be able to explain to me what would happen if I added more B to this reaction. What would happen to the concentration of each chemical and the KEQ, something we didn't get into yet. And then draw and explain what makes an acid or a base, acid or a base. What's different about the two things? Because one isn't as famous as the other one. This would be a good time to pause me, write down the questions, try them out, see what you know, and then we'll take them on together. All right. Get rid of my big ugly head and see if we can work this out together. Now, if you look at this reaction, you can see it's really, really simple. A plus B makes and breaks C and D. And you can see one thing about it, the forward reaction is endothermic. It's building an uphill battle. So always think about energy. The other things that we should recognize about this, of course, is I'm saying they're going to change something. I'm going to add more B. So if I'm going to do that, I'm going to increase the amount of B. Now, if you know your Le Chatelier, that makes it easy. If I add, it should move away, right? This means it's going to shift the reaction to the forward reaction to favor it. And that kind of makes sense because what I'm basically doing is I'm adding more B, so B is going to collide more often with A, and that's going to make more C and D, right? That also means that if I'm making more C and D, that's going to destroy the A and the B eventually to bring down their concentrations to make the C and D. So that prediction should be easy by this point, right? So when we look at this, one thing we should recognize is I can think about this like this. If I look at the KEQ is always going to be the ratio of the products over the reactants. I got C and D are on top, right? I got A and B on the bottom. Those are my reactants. I just increased the amount of B, which then created more C and more D, and it destroyed the A and the B eventually. So what happens to the KEQ? Well, the cool thing about it is the KEQ stays the same, right? It stays exactly the same because the KEQ is really just the ratio of the products over the reactants. Now, a way to think about this would be this. Say that I took and I had myself a teeter-totter, right? I increase the amount of B. That's going to decrease and destroy some A, right? That's going to shift it as it runs into and collides with A and B collide together. That's going to produce more of the products, the C and the D. Their concentrations are going to go up. And then what happens? Because that's going to definitely shift it and change the balance. Well, then there's going to be more C and D. And C and D will now collide more often, which means they'll destroy each other to make more A and B until eventually, of course, later on, it will make its way back to equilibrium. And that's crucial because as C and D bounce into each other, it's going to eventually get to the point where it's making and breaking at the same rate. And their concentrations won't be, of course, the same concentration they will be before, but the ratio of the reactants to the products will be exactly the same ratio because it's all at the same temperature. So you can shift it temporarily. This is a temporary shift with things like concentration. And concentration changes can temporarily shift it because, of course, you can change the number of collisions initially. But then, when you make products collide to make reactants in the reverse. So it balances itself out. It's like the universe resisted change, right? Resistance change. So if we look at this, one of the things that we can see about this is there is one way that you can actually shift it more than just temporarily. The only thing that can change it permanently is a change in temperature, right? That allows you to change the KEQ. That's why anytime you're given a KEQ in a problem, it always says at 245 degrees or at 373 degrees because the temperature decides where the equilibrium point is because it's the thing controlling how fast they collide. And that's kind of a big deal. That's why temperature goes with KEQ, and that's how you can shift it permanently, but that's why so many chemical reactions involve adding heat or taking away heat because we want to shift it to make it what we want, right? Now, what does this mean for us? This is kind of crucial when we think about the Earth, right? Now, this has anything to do with real life. It's just chemistry. But let's say that humans decide to do a process where they really like to make, say, CO2. Say we like to combust stuff, and we suddenly burn up a lot of that CO2, and we produce tons of CO2 on Earth. Now, a lot of people are concerned about that, going to the oceans, going to the atmosphere. And, well, that's a new chemical. That's going to shift things, but it's only temporary, right? Well, the problem with this is, of course, is that CO2 has properties with its double bonds that it likes to store heat. It's a greenhouse gas. And it acts like a blanket that holds the heat onto the Earth. And unfortunately for this one, it not only changes concentration, it also changes the amount of heat that's stuck on Earth. So it increases the temperature. And that's a big deal because temperature changes cause huge shifts in equilibrium, right? What this means is this would warm up the entire Earth, the oceans, the land masses, the atmosphere. All those areas, of course, are chemical reactions. Living things are chemical reactions. And what this would effectively do is shift all of the reactions on Earth. And that's why scientists are concerned about global warming. Because global warming, of course, is caused by this holding on to the heat, by the extra CO2 and methane especially, right? And that's a big deal because global warming leads to this other process called global climate change. That's where it doesn't rain enough in some places, or it rains too much in other places. There's more hurricanes and cyclones and erratic weather events, and ocean levels rise because, well, all those processes are tied to chemical reactions and, physical reactions, stuff like melting and evaporating, so that if you change the amount of heat on Earth, you have a huge impact on the rate at which reactions happen, and a lot of species cannot keep up with that rate of change. We think we can, but not without the other species. So, one key thing that we should notice is that's why it's so important to understand Le Chatelier and to understand that changes in temperature have huge impacts on the results that will come through in chemical reactions, because the Earth's going to find a balance, and it doesn't care if it finds a balance with us or without us. It's just about balancing out the rate of collisions. And there are more collisions because there's extra heat on Earth, right? Yay, chemistry. It could change the world. And it is because of what we're doing with the world, right? Now, other part of this, of course, can attach into an article that we normally read where there's this weird chicken drinking soda, right? There was a problem down south. It was really, really hot, and they grow a lot of the chickens that we use to eat eggs. And one of the problems they ran into was the chickens were getting hot. Now, chickens can't sweat, so what they do is they pant really fast. And as they pant like a dog, they evaporate away water to cool themselves off. But at the same time, they also are breathing faster, so they, of course, breathe out their CO2. And that's a big deal because that means CO2 is leaving their body. They're decreasing the amount of CO2. With less CO2 there, that's a big deal because normally in their body, what CO2 does is it goes into solution. It becomes this stuff called carbonic acid when it mixes with water. Being carbonic acid, it dissociates. It does some proton football, and it makes into their body, of course, these things called carbonate ions, which can then smack into calcium ions to make their shells, calcium carbonate. The chickens were laying really fragile shells because they were breathing out all their CO2, which means, if you understand Le Chatelier, if I take, then it moves away. And what it was doing was it was destroying the calcium carbonate of their eggshells in their bodies to make the carbonic acid so that it could produce the CO2 so the CO2 could collide enough times. So these farmers figured out, hey, I'm losing money because the eggs keep breaking. They're too fragile. So what they did was they fed their chickens soda. You guys call it pop. They gave them carbonated water. And the carbonated water, of course, has a higher amount of CO2. So by pushing CO2 into them, if you add, it moves away. And that's essentially what they did. And that allowed the chickens to make more calcium carbonate. Now, this becomes a really big deal because this is a chemical industry and almost everything you eat contains eggs in it these days. And this is just one more example of how temperature has a huge effect on industry because chicken eggs and every other chemical process we have relies upon temperature. So they're having even more trouble now because the Earth's temperature is increasing and extra hot chickens put out more and more CO2 as in their breath. And that means their eggs get more and more fragile. So they've got to compensate for that. Good thing they understand. Le Chatelier. You call me chicken? Yeah. Makes sense. I mean, the French love their chickens. Now, roosters especially. Now we need to talk about these things called acids and bases. So let's talk about acids first, right? Because it's definitely tied into what's going on with that planet. And a typical acid that you have in your tummy right now is called hydrochloric acid, right? Now that is a solution, as all acids are when they're active. and that is aqueous. It's mixed into water. Now, crucially, that means that when we put it into water, what does it do? Well, it formerly, of course, was this chlorine and a hydrogen, two nonmetals, sharing together, but they're not sharing equally. They are, of course, in a highly polar covalent bond. That's because chlorine is hogging the electrons. The hydrogen is just holding on. As soon as I put it in aqueous, I put it into water. And the water, of course, is a crucial ingredient because that allows it to dissociate. A good acid like this one, because hydrochloric's pretty nasty stuff, a strong acid, it'll kick off these things called protons. Now, they're hydrogen ions as we've been calling them, but from now on, I'm just going to call them protons because that's what they are. They are hydrogen ions. It's the same thing. Essentially, they've lost their electrons, so they're just the nucleus, a proton, a single proton for hydrogen. Included with that, of course, you get these things called chlorine ions, and those chlorine ions would be aqueous as well. When they come out, they're just chlorine ions, right? So we can call them that. Now, this is what happens typically with acids, and the first guy to notice that was a Swedish guy named Arrhenius. And Arrhenius was also the guy that predicted in the 1700s this thing called global warming would be caused by CO2. Must have known something, right? Now, Arrhenius had a definition of an acid, and it's a really good one. It's not the best one, but we're going to use it, right, because it's a common one that's known. And he said that an acid is a substance that produces protons in water, right? And don't forget that a proton is a hydrogen ion. It's the same thing. So anytime that I'm looking for an acid, what I look for, of course, just like when we did naming, is I look for the H. Well, that means it has protons that it can, of course, produce when you put it in water. The opposite of an acid are these things called bases. So let's take a look at a base, right? A typical base that's a pretty strong one is something like sodium hydroxide, right? Lye. And sodium hydroxide, of course, to be a base, you have to put it in water. Now, sodium hydroxide has a metal, a sodium ion. It also has, typically when you see bases, we notice them with these things called hydroxide groups, right? And OH1 minus. And notice the minus is on the oxygen that's there. And they'd actually be covalent bond. They're strongly tied together. As soon as I put it in aqueous, it's in water, right? So what's it going to do? Well, if you look at your solubility chart, you know that hydroxides with sodium, it's a group 1 metal, they're going to dissociate. They are soluble, right? That's going to put sodium ions into water. It's also going to put hydroxide ions into water. Notice how when you write it, now the negative goes behind the H just by convention, right? Because the oxygen must be important here, right? That means that they are dissociating to make those sodium ions, and they're dissociating, of course, to produce in the solution these things called hydroxide ions. And I'm trying to draw it carefully there. You can see that they're overlapping because they're strongly held together. They don't want to give up. This is my hydroxide ion. And typically already this year we've learned that when you see a hydroxide, hey, that's a base. You see a hydrogen, that's an acid. Well, Arrhenius is the guy that noticed this first. He's got a weird spelling to his name, Arrhenius, right? And he had a definition of a base. I'm all about that base, If we look at the base, a base is a substance, Arrhenius said, that produces hydroxide ions in water, right? And of course, hydroxide ions are the OH1 minus. Hey, an H and an OH. Hey, it always involves water. This must have something to do with water. No wonder water is so important for all these things, like it is in all in chemistry. It's like a catalyst or something, right? So, cool thing, of course, you see an H, you know you're looking at an acid. See an OH, you're probably looking at a base, right? But it gets a little more complicated. That's why there's other definitions. But now you know Arrhenius's. It's all about producing, of course, hydrogen ions for an acid and producing these things called protons in water. Hydroxide ions in water for a base. So if we look at this, you deal with acids and bases every day. For instance, you look funny and I look funny because this thing called deoxyribonucleic acid, DNA. We are made of acid and bases and acid-base reactions. So you should be able to name at least 3 household acids and bases that you can think of, and we'd be looking at them in our lab, right? Some of them you eat, like citrus fruits, citric acid. Others you use to clean, like bleach, but people don't really know if it's an acid or a base. They just know that it's nasty and can kill you and you shouldn't inject it. And there's the stuff like soap. Hey, and tums, and an acid, because sometimes you have heartburn, right? Or Alka-Seltzer. Hey, it starts with Alka. Must have some, beautiful metals inside of it. Must be like a basic solution. So what we do normally in our class is we look at different ways we can identify acids and bases with common household things like soda or drain cleaner or ammonia. And we'd be doing these things called blue and red litmus tests. And you'd figure out what they mean in terms of if they change a color. You'd be using a pH sensor to get a nice reading off those things. And we often use red cabbage juice because it's an indicator. And we would carefully find out and try to identify which ones were acids and bases based on the data that we have and what we know previously, right? And like a mad scientist, we would make sure that we had our goggles better placed over our face, because which can burn your eye out? Both acids and bases. They're both dangerous for you, right? So cool thing. Now, after we did that quick lab, we'd get out our notes and we'd figure out what was going on. Well, the cabbage juice is an indicator, and we can see that we use this pH scale. We'll get into that in a second. The litmus paper is nice because it can change color to tell you what the pH is, whatever that means. Cabbage juice, of course, is a solution that contains this stuff called anthocyanins, the purple stuff in there. The neat thing about it is if you mix it with a whole bunch of protons and acid, it changes the structure slightly, which makes it reflect and absorb light differently, which makes it turns a red color. And red tends to signal acid. Think of burning flesh and blood, right? Whereas if we put it with a whole bunch of hydroxide ions, that means that it will be basic, and that changes the structure once again. And now it'll absorb and reflect other light and turn blue. So you can kind of think of like blue is for basic, red is for acid, right? Now, along with that, you, of course, ingest acids all the time because they tend to taste, sour and tart. So if you look at something like soda is carbonated water. It has carbonic acid in it. And it also, if you look at the instructions, has phosphoric acid in it. And those, of course, give it the flavor, but that's also why I don't drink soda, because my teeth are made out of a base, and I don't want to eat away at my teeth, right? Citric acid also is a common combination with things like citrus fruits. It gives it that nice lemony or orangey citrus flavor because, of course, it is an acid, and that's one way we can identify those things. Bleach, sodium hypochlorite, is found in things like swimming pools. And why do we put it in there? Because bleach is nasty. It is a very strong base. So this thing, of course, loves to steal protons from things like your eyeball. That's why it stings, but it especially does it to bacteria, so that when those little kids have been swimming in the pool, they don't know about the don't put your pee in the pool thing. They basically help to kill off any bacteria that's in there so you don't get sick, hopefully, right? So bleach is a base, and it's pretty good proof that bases can be nasty too and can hurt you. So if we look at this, properties of acids and bases, you should write this down. Acids tend to be sour. Think of Sour Patch Kids. They contain citric acid. Acetic acid, of course, we can consider that like vinegar. Bases tend to be bitter. Good examples of that would be like soap or baking soda. They feel slippery because they actually are grabbing those protons, and that helps to mix with the solution and make your oil slip away from your skin. So detergents like ammonia are basic as well. The reason they feel slippery is because they're attacking those oils in your skin, right? So you can see lemon juice and things like citrus fruits, and then baking soda, Drano, cleaners, they tend to be basic solutions, whereas the acidic ones we tend to have in our food because, they taste good. They're sour. The pH scale that we need to know. Oh, pH. Weird. There's a big H. Hey, it must have something to do with hydrogen. If we look at this, of course, it's on a scale that goes from 0 to 14 with 7 dead in the middle. And hopefully recognize that once you go below 7, it becomes acidic. 7 itself is the neutral zone, right? And above 7 is basic, so up to 14. When we look at common chemicals that fit in this category, the easiest reference for you is pure water is neutral. It's got a pH of 7. Must be something magical about that 7. We'll get into that later. As you start to have more and more of those hydrogen ions, like milk actually, people are like, oh, drink milk, it's basic, it'll cancel those hot wings you ate. It actually doesn't do it by being a base because it's slightly acidic. It's the mucus in the milk that helps to coat your throat and your stomach so you don't have that heartburn. Then as we go from bananas to tomatoes, you can get a lot of heartburn with those, all the way to stomach acid, which has a very low pH and is very acidic. Well, it's kind of nice. That kills off the bacteria that try to come in with your food, right? If we look at folks that like to suck on lemons, those lemons, of course, can eat away at your teeth. But if you're old, that's all right because your taste buds are dying and your teeth are probably gone already, so you can suck on the lemons all you like. As we move up into eggs and baking soda, of course, these are fairly weak bases, all the way up to things like soap, ammonia, and bleach, which are strong bases. So you don't want to put any of that, of course, in your stomach or inject it at all. It will not help you. It will simply kill you while it sterilizes everything too, right? Science. It's good for somebody. What about ammonia? Now, ammonia is NH3, and it's got a lot of H's in it, It's a base. If you take the pH of it, if you measure it, how can that be? Well, this all comes down to the fact that there's a problem with Arrhenius's definition. It's a good definition, but you have to think about it deeper. So let's look at this. There's a better definition called the Bronsted-Lowry definition of an acid or a base. And I prefer it because it's much straightforward and they're both correct, but this one's the easiest one to understand. What Bronsted and Lowry said was they said that an acid is a proton donor. I like to think about it like a quarterback. It throws out protons, and it's the protons that burn you. A base is a proton acceptor. It grabs onto protons because it usually, pulls them out of solution. And OH is pretty good at doing that. So a good example of this would be something like this. A basic example is, let's say we got HA. It's a fictitious acid, right? If we take that acid and we put it in the water, it will dissociate and throw its protons out, and the water will, of course, grab onto it. When it does that, here's a key thing. They take on different roles. The HA is my acid because it's the proton donor. The water becomes my base because it becomes the proton acceptor. What it becomes, of course, is this thing called a hydronium ion. It grabbed onto that extra proton, and now it becomes the new quarterback. It has the proton and can throw it out. So we now call it a conjugate acid. It was the base. It's now become the conjugate acid. And that's how it always works here. It will always switch roles, right? At the same time, the thing that was the acid now becomes the new thing that could take the proton back. It becomes the conjugate acid because you'll notice in all acid and base reactions, they are reversible. But that's why we studied equilibrium first. Whichever way they favor decides, the strength of the acid. So if we look at this, this is the story of Proton Football. So sketch this out because it's very, very handy. I wish we could play it in class right now, but that's life. We've got, of course, in football, a quarterback and a receiver, right? What the neat thing is the quarterback and the receiver, they can play a little ball, and that allows them to throw the ball, and then the quarterback, once they lose the ball, they throw it to the other person. They become the new receiver, and the former receiver becomes the new quarterback. It's reversible. You can play catch back and forth. That's what's going on with acids and bases. So a good example of this would be like a quarterback, like a strong acid, like hydrochloric acid, and a receiver, like water. If I look at those, they can throw the proton. That would lose the proton from this, and then the hydrochloric becomes the new receiver, and the water becomes that hydronium thing. It becomes the new acid. We call it conjugate acid. So notice in this case, the acid, the HCl, is throwing the proton to become the conjugate base, the new receiver. At the same time, what was my base, my proton receiver, the water in this case, becomes my conjugate acid, the hydronium ion, a water with a hydrogen stuck to it, the new quarterback. And this cycle, of course, tells you which way it will go. This one tends to favor the forward reaction because it's a really good thrower. That's why hydrochloric is a pretty strong acid, right? Which we can get into deeper. So proton football, gotta love it. Now, ammonia is a proton acceptor. And by Bronsted-Lowry, that means it's a base. What this means for us is, of course, if we take ammonia and we throw it into water, it will, of course, take on the proton from the water and become this thing called ammonium ions, and the water will become a hydroxide. What's happening here is, of course, they've changed their roles. The water starts with an H, and most people naming notice that, hey, the water is an acid in this case. It starts with an H. Hey, we just said it was a base before. Wait, now it's being an acid? That's why water's awesome. It could be either a acid or a base. It can do both. It's the beauty of water once again. When we stick it with a base, it acts like an acid. So if we look here, this gobbles up and receives another one of those protons and becomes the conjugate acid. So once again, base always becomes the conjugate acid. At the same time, the acid, the water, lost its proton and becomes the new receiver. Hey, that just put hydroxide ions into solution. That's Arrhenius's definition, a chemical that produces hydroxide ions in solution. And that's what happened here when it grabbed that proton. So both definitions work. I just prefer Bronsted-Lowry because it's proton football and pretty straightforward, but they both apply because they both basically go with the same idea. An acid will provide protons into a solution or produce them, and a base will supply hydroxide or produce hydroxide ions in solution. So they both work. They're both great, right? Now, cool thing about this, of course, is normally we go up the household acid and bases lab and go after a little bit of text homework. You're going to get an assignment from me from the remote time. So the biggest thing that we need to be able to recognize here, of course, is what acids and bases are. If we ask Arrhenius, Arrhenius will say that an acid is a substance that produces hydrogen ions, protons in solution. Bronsted-Lowry would say it's a proton donor. So those are very similar. If we look at Arrhenius, he would say that a base is a substance that produces hydroxide ions in solution, and the ammonia certainly does that. Or we can go Bronsted-Lowry and say, hey, ammonia is a base because it's a proton acceptor. Either way, it's proton football, and whoever was your acid will throw the football and become the new base, the new receiver. And the base will be the football catcher, the proton acceptor, and become the new acid because they can go back and forth. And this one, of course, tends to produce quite a few of those because ammonia is a fairly strong base. Not the strongest, but it's fairly strong, right? Cool. That was pretty basic.